All right, so what I would like to do is actually start by looking at this example 4, which is based on the ebook. And so what I'd like to do is focus in on geometric, like picture linear transformations to give you an idea of what some of these things can actually look like. To do that, I'm going to switch off of this particular share screen. So I'm going to the ebook, which you can access through my lab. I actually downloaded the file so we could work with it. This is supposed to describe the unit square, and then we're going to ask ourselves what happens to that unit square, that picture of the fish underneath the transformation. And this is in the book, so all of you can play with it on your own. So notice that if you use the identity matrix right here, what does the fish change under the identity transformation? No change. So if we want to reflect across the x1 axis, which would be the x-axis, so you'll notice if we're reflecting across the x-axis, then it's like we took all of the y values and we turned the y values into negative y values. And so that flipped our fish. Sounds like a weird band name. Flip your fish. Flip over the x2 axis or the y-axis, and all your x's are going to become negative. And so you're getting this mirror image happening. If you're just joining late, I'm having Zoom camera issues, and so my camera keeps cutting in and out. So I'm not trying to ignore you. My hair is no worse than normal. We could reflect across the axis. So here, notice I swapped my x's and y's. And so on the left, you had the fish aimed swooping right to left. And now you have it swooping kind of top to bottom. Same thing. And so what I would encourage you to do is come here, play with this on your own, and try to make these connections. You want to be able to look at this matrix and think, that's a reflection in x1 equal to negative x2. You want to be able to make that connection yourself. Keep going. So yesterday we talked about contractions and dilations. And so we could contract horizontally. And notice what we're doing is we're stretching things out. We could squash it all the way to 0. If we had a negative horizontal contraction, it's almost like it flips it over. Just like this is one of the reflections that we did earlier. And notice that what's happening is, in this case, is we're doing a horizontal expansion, and what it's changing is the entry, is that 1, 1 entry. We could do the same thing vertically. Again, what I want to point out is if we're vertical, we're doing this vertically. In this case, we're expanding by a factor of 2. And what's changing is that entry up above. I'm hoping you're getting a picture for what we mean by a geometric linear transformation. A little bit more complicated version is the shear transformations that we were talking about yesterday. And so notice there's a little bit of a pun happening. This is a shear transformation. And then what are we talking about? Yes, that's right, Megumi and Felix. We're going to shear the sheep. So who says that textbook authors and mathematicians don't have a slight sense of humor? So what are we going to do here? If we want to shear it horizontally by a 1, what I'm going to do is it's almost like I'm going to grab the top of the picture. See if my camera will work now. My camera's working at the moment. I grab the top of the picture and I shear it across. Like I'm just holding the bottom fixed and I'm moving the top. I'm moving 1 to 2, you know, like almost like doubling it. Here's 1, 2, 3. So the point started here and it moved over by 2, or by times 2, maybe you could think about it that way. And this point here moved to right there. I guess it's +2. I guess it's plus, not times. Kind of like right there at the top. And then everything else is sort of proportional. So these would be a horizontal shear. So it's horizontal by a 2. And notice what that's impacting is it's impacting kind of like the X row, if you will, if you want to think about it that way. If we do it vertically, now we've got it vertical by 2, and we're kind of impacting almost like the Y row a little bit, if you want to think about it that way. This is a little bit harder to see what's going on. In this case, we're going to project the entire cube onto the x1, x2 plane, or the xy plane. We could also project onto the xz plane. So if I'm going onto the xz plane, that's because here's like x, or if it's your old world, maybe you think about it like it's the I unit vector, and here's your z, or your k unit vector. And so we're saying, okay, we want to project it onto the xz plane. So there's a projection, and we're changing dimensions in that particular case. And again, these animations are all available to you in the ebook in my lab. So here's probably the most important, and the one that will take us a little bit longer to derive. We can make our fish rotate. So you'll see the 1/3, 2/3, 1. What that's talking about is 1/3 pi, 2/3 pi, 5/3 pi, 2 pi, something like that. And so here I took this line right here, and I rotated it around counterclockwise by 4/3 pi. Something like that. If you want to remember this, like one way of abbreviating this would be its cosine along the diagonals, and then it's negative sine and sine. Like a shorthand way of remembering it. So I want to figure out where these linear transformations came from. And so let's start right at the top. So example 1, the columns of I2, so remember I refers to the identity matrix. The columns of I2 equal to 1, 0, 0, 1 are E1, 1, 0, and E2, 0, 1. So in the old days, you would have said something like I is equal to 1, 0. But that was so last quarter. Now we will call this, we would say this is E1, and we would write it as 1, 0. Or E2 instead of J, and we'll write it as 0, 1. And the context will tell you what's going on. But if we had an EI, that's kind of funny. This would be saying that you have a whole bunch of zeros, and then a 1, and then a whole bunch more zeros. And that 1 is going to live in the jth row. The number of total entries in the standard basis is going to be known by context. Like context will tell you whether there's 2 rows or 5 rows or 50 rows or something. Everybody okay on the E's? So suppose T is a linear transformation from R2 to R3 such that T of E1 equals 3, 2, negative 5, and t of E2 equals 0, negative 1, and 9. Find a formula for the image of an arbitrary x in R2. So first of all, let's look at our E2 and our E3. I just want to do a little bit of scratch. So, I said E2 and E3. I meant E1 and E2. So 1, 0 or 1, 0, 0. What do you think? Oh, did I say Jath? And I should have said Ith. Good call. I'll fix that in a second, Andrew. So it's 1, 0 from Felix. That's correct. It would be this first one. And the reason it's the first one is because our transformation is starting in R2. So let's see if we can figure out what's going on here. Erase all this junk. Andrew pointed out that over here, I said Jath. I should have said ith row. So if I want to find a formula for an arbitrary element, I'm going to start with my tx, and I'm going to recognize that I can write my x as x1 e1 plus x2 e2. Let's see what we got. What's going on here? So here's my x. What is that x? So we have x is equal to x1, x2. So t of x would be the same thing as t of x1, e1 plus x2, e2. Is that obvious? Let's make sure that you're seeing what's going on here. This would be because this would be x1 times 1, 0 plus x2 times 0, 1, which is a funny way of writing x1, x2. That's why this is the case. So now this is which kind of transformation? What's our keyword here?
Linear.
Thank you from Sammy, Abe, and Felix, and whoever was talking, whose name I didn't get to identify. Thank you. So it's a linear transformation. And so since it's a linear transformation, we can use our property from yesterday and say this is equal to x1 t of e1 plus x2 t of e2. So this is property, or the property of a linear transformation. And so I think we were given t of e1 and t of e2. So this would be x1 times t of e1 was given. From Abe, yes, we're only dealing with linear transformations. Yeah. T of e1 is 3, 2, negative 5. This was given, plus x2 0, minus 1, and 9. And this is an example of what? So we took this is an example of a linear combination. And since it's a linear combination, we can combine it into a product where we have 3, 2, negative 5, and 0, negative 1, and 9 times x1, x2. So this thing right here, this A, come on, little buddy, it's just not my day. A, this is the matrix of the linear transformation. So this shows us that if we know T of E1 and we know T of E2, that they can give us our A matrix. So our A matrix is going to have T of E2 is going to be the second column. T of E1 is going to be the first column in that matrix of the linear transformation. More generally, like this is kind of like a specific case, but more generally, what we're saying is that if A is going to be, well, if T is a linear transformation, then T of X is going to equal AX for all X in Rn. So there's always a matrix. And the jth column is T of, is T of EJ. So where EJ is that jth column of the identity matrix. Or in other words, A is equal, the linear transformation matrix is created by figuring out what happens to the standard basis vectors under the linear transformation. So this matrix A is called the standard matrix for the linear transformation. So example 2, find the standard matrix A for the contraction transformation T of X equals 1/2 X for X in R2. And so what we need to do is we need to find T of E1 and T of E2. So this would be like saying, so remember E1 is 1, 0, and E2 is 0, 1. And if this is a contraction transformation, what are we going to do with our X? What are we going to do to it? I'm going to multiply it by, from Alex. Yep, we're just going to multiply it by 1/2 because that's the transformation that was described. So this gives us 1/2, 0, and 0 and 1/2. Okay. So that's the first step. The second step is to construct your A. So remember, A is going to be the matrix made up of T of E1 and T of E2. Oh my gosh, so not my day. So T of E1 is this guy right here, is just we found before. So 1/2, 0. And then T of E2 is here, 0, 1/2. And so what we're saying is, so our conclusion is that T of X equals AX with our A equal to this matrix that we just found. So the next question asks us to do the same thing. And here we've got to do a little bit of geometry. So let's think about what's going on. So we're going to do a rotation. And so if we started at the point 1, 0, that 1, 0 is going to go to point here where we've rotated. Is that psi? Never remember which Greek letters is psi, phi? think that's psi. What are the coordinates of this? Oh, it's phi. Thank you, Ahmed. So what are the coordinates of this point here? Think on the unit circle stuff. So it's going to be cosine phi, sine phi, sine phi. And so we can use that concept to say that if we're in our first step, we want to find t of E1, and it's going to be cosine phi sine phi. Should have used a different color there. Should have used my light blue color there. Then to find t of E2, we're going to start at 0, 1, and we're going to rotate around to this other point. What's the total angle that's been swept out here? If you think about from the positive x-axis that we know of. This would be like sweeping out pi over 2 plus phi. Yeah, pi over 2 or 90 plus phi. So this point would be at cosine pi over 2 plus phi, comma sine of pi over 2 plus phi. So that lets us figure that t of E2 is equal to cosine of pi over 2 plus phi and sine pi over 2 plus phi, which is we can use a trig identity on this because this is like cosine of a plus b and sine of a plus b. Anybody remember this one? Cosine of a plus b is like cosine of a cosine of b minus sine of a sine of b, something like that. If somebody knows it, could somebody put the sine version of this formula in? That'd be cool in the chat. So, cosine pi over 2 cosine phi minus sine pi over 2 sine phi. I think the sine version is flip-flop, so I think it's sine pi over 2 cosine phi minus sine phi cosine pi over 2. Did I flip-flop that? Ooh, I have it backwards. I'm sorry. I have this exactly backwards. It's sine phi. Maybe it wouldn't make it. Maybe it wouldn't make a difference. Never mind. Anyway. Okay. So how do it? And it's a plus. Thank you for that, Felix. Because it's change. Cosine is with a C. Change. Sine is with an S for same sign. And so good news about all that garbage. It starts simplifying. The cosine of pi over 2. The cosine of pi over 2 is 0. The sine of pi over 2 is 1. And so all this stuff simplifies to like negative sine phi and cosine phi. I think that I'm okay, Elijah. I think it does. In retrospect, I don't think it makes a difference. I think it would have worked either way. Because there was a plus, not a minus, so it didn't make a difference. This ends up being the orange stuff. So we're going to put the t of E1 and the t of E2 together into our second version. So second, remember you're going to have A is going to be equal to t of E1, t of E1, t of E2. And that will be cosine phi minus sine phi, sine phi, cosine phi. And so our conclusion is that the matrix of the rotation matrix, so you have this t of x equals ax, and your a is going to again be, like we said earlier, cosine minus sine, sine, cosine, just like we said before. So we're now going to shift gears. So we're going to shift gears here, and we're going to start talking about a little bit of theory. So before, what we were looking at earlier was like what does a linear transformation look like geometrically? How would you find the matrix of a linear transformation? And now we're going to talk about some of the terminology or the theory that goes with it. And so in the past, we've talked about things like functions and domain and range, and we've talked about functions being invertible, things along those lines. Here, we're doing those same things. We just have a new set of vocabulary sort of to accomplish the same thing. So a mapping T from Rn to Rm is said to be onto Rm if each B in Rm is the image of at least one X in Rn. Another way of saying this is saying that the range of T is all of the codomain of Rm. Let's look at two examples from the past. Here's a quadratic like y equals x squared. And here's y equals x cubed. Come on. So what's the range of the quadratic y equals x squared? What's my range here? So my range is positive y, or y is greater than or equal to 0. So my range would be y is greater than or equal to 0, or maybe I could put it this way. My range is not all real numbers. So it's not all real numbers. And so here we would say that we are not onto, because our range didn't fill out all possible y values. On the other hand, if you look at y equals x cubed, your range is all of r. And so this would be an example where it is. So yes, it is onto. Here on the left, you have an example that's not onto because we're not filling out all of that codomain. And on the right, you have an example that is onto because we're filling out all of the codomain. The range is the same as the codomain. Okay, so this is the concept of onto. When we pick this up again on Tuesday, we will talk about the concept of one-to-one. And one-to-one is basically the thing that you've been playing with all the time in the past, where you're trying to figure out if a function is invertible. And so you had the old horizontal line test. Maybe you remember that. So that's what's going on with one-to-one. All right. And now we're going to look at a definition that's perhaps a little bit more familiar, and that is the idea of one-to-one. And so we'll say a mapping. And remember, mapping is kind of like code, in this case for function. So a mapping T going from Rn to Rm is said to be one-to-one if each B in Rm is the image of at most one X in Rn. In the old days, this was the horizontal line test. Come on. Come on. Doesn't like me. I did I did upgrade OneNote, and clearly it has not fixed all of my issues. But thank you for that suggestion for everyone. So horizontal line test, you think about the old days, you take like a quadratic, something like this, and you'd pick a value here, and you'd notice, boom, it crossed. So there was one, like, how do I show the picture here? You think about your range, and there's this one y value that's here, and you've got your domain, and you'll notice that there were two different x's that are going to the same output point. So this would be an example of a function that's not one-to-one. Okay. Okay. So that's what this picture's doing, and I'm just trying to tie it in to what we've done in the past. Is there anybody that I'm still struggling to find somebody that comes in early-ish that can help me be a co-host to help let people in off the out of the waiting room if they need it. So still looking for a co-host. The ideal person has reliable internet and is usually here a couple minutes early. And so you can Slack me or DM me or whatever. But that will help the whole class out. All right, so let's look at a theorem. And the point of this theorem is we're going to introduce a new little proof concept. So theorem, let T go from Rn to Rm be a linear transformation. Then T is one-to-one if and only if the equation T of x equals 0 has only the trivial solution. Let's make sure we're tracking some of our vocab. So this will be our claim here. And then we're going to do our proof. This is a if and only if proof. And so there's a couple ways of doing if and only if proofs, but one of the ways of, do you not know SAAG? How do we do an if and only if proof? Sort of like the two approaches. So from Felix, yeah, we're going to prove this in both ways. And so we're going to prove it going left to right, and then somewhere down below, we're going to prove it going the other way, right? It doesn't have to be this way, but this is the way we'll approach it today. Okay, so that's one thing. And then remind me again, it says trivial solution. What's the trivial solution? It's 0. And in this case, I'm going to go with Croy because it's specifically because it's the 0. Which 0 is it? It's the 0 vector. Exactly. It's the 0 vector. Thank you, Megumi, Croy, Felix, Alex. All right. So if we're proving from left to right, notice that we start on the left and it says, then T is one-to-one if and only if. So I'm going to start by assuming that T is one-to-one. That's not 1 minus 1. That's just shorthand for one-to-one. Okay. So we know that t of 0 equals 0. And we know this because we're given that t is a linear transformation. So linear transformation. That's how we know it. Yeah, it's linear transformations are always lines through the origin. Okay. And so this implies that t of x has a solution. Sorry, t of x equals 0. Okay. So t of x has a solution, and it must be something since t is 1-to-1. So if you know that your transformation is 1-to-1, what can you tell me about the solution here? 0. Oh, and not O. I think you're just giving me a hard time there. Let's see. So what can you tell me here? So since it's solution, maybe go back to the picture for a second. So if it's 1-to-1 and you have a solution, so maybe here's my solution. How many things went to that solution? Yeah, just one. And specifically, if our output is 0, then we know that our input is going to be 0 as well. Okay. So t of x equals 0 has a solution, and it must be unique. It must. Since t is 1-to-1. But that's what we're trying to show, right? The question said, if t is 1-to-1, and then the equation t of x equals 0 has only the trivial solution. So this implies okay. The function be 0 times x. No, it couldn't be 0 times x because it's 1-to-1, and that function 0 times x is not 1-to-1. And thanks, James, for adding unique. All right, so we've done one direction. Now we got to go the other direction. And so we're going to start with here, the equation t of x equals 0 has only the trivial solution. And we're going to try to show that if t of x equals 0 has only the trivial solution, then t must be 1-to-1. So here's where we're going to do something new. So what we're going to do is we're going to do what's called like a proof by contradiction. We're going to assume it doesn't work and show that we get that something happens as false. So we want to assume that t of x has only the trivial solution, and we're going to try to show that it's 1-to-1. So let's suppose that it's not 1-to-1. Okay. So we think that it is going to be 1-to-1, but let's just suppose that it's not 1-to-1 and see what happens. Okay. So if it's not 1-to-1, what does that mean? If we go back to our picture, if it's not 1-to-1, that means that there are a couple of different points here, like boom, there and there and there, that are all mapping to the same point, right? There's multiple inputs that can get you to the same output. Okay, at least one time. There's at least one of those. So suppose t is not 1-to-1, then this implies that we have this backwards e. What's the backwards e mean?
There exists.
There exists. Thank you very much. So it means that there exists a u and v that are not equal to each other, and a b such that we've got t of u equals b and t of v equals b.
Dusty, if even though it's not one-on-one, do we still have a unique solution or not?
We're going to try to show that the solution is unique. We're going to try to show that this is going to fail, basically. Yeah. Let me make sure you're seeing what's going on here picture-wise. So you have your domain, and you have your range. Somewhere here you have a range. And there could be lots of points over here where things are happy, where they're 1-to-1 in certain instances. But there's this b, which is like a special point in here. That's our b. And there's a u and a v that live over in this domain. And they both map to the same point. Maybe I could change my color here. They're both going to B. Okay. So that's what we're supposing. Suppose that this is the case. Okay. So, that's great. We can use some of those properties of linear transformations. And so now we could look at t of u minus v. Okay. So t of u minus v would be t of u minus t of v, because it's a linear transformation. And we know that t of u equals b. And we know that t of v is also equal to b. And so this must equal what? This equals 0. Thanks, Seche and Felix and Juan and Megumi and Croy and Seche. All right, so let's see. What does that mean? But what did we just assume? What did we assume right at the very top? we assume that we had only the trivial solution. So what does that tell us about, so t of x equals 0 has only the trivial solution. That's telling us that your x is the trivial solution. And so here we have t of u minus v equals 0. So what does that tell you about u minus v?
X vector?
So they would be our, that's right, they would be our x vector, and it tells us that they must be 0.
Be 0, yeah.
Yeah, exactly. But what did we assume? What do we know about those u and v? Like, we got a problem.
Equal.
We
Yeah.
have here, in one place we say they're equal, in one place we say that they're not equal. So we have a contradiction. So you have an arrow pointing at another arrow. So this means it's a contradiction. Okay. Again, it's kind of a little bit of a hard thing to draw. So let me put it in the chat what the symbol is, in case you're not reading it right or seeing it right. So it's like, two arrows pointed at each other. From Seche, is there a way we could use this for the first part of the proof? I don't know. I'd have to think about that. It's a good question. So it's a contradiction. So what was our assumption that we made here? We suppose that t is not 1-to-1 in order to get to this contradiction. So that tells us that t must be 1-to-1. Because if it wasn't 1-to-1, then we had a contradiction. I think it must just be another vector. Yeah, and we showed that u minus v must be 0 up above. So therefore our claim is proved. Therefore t is 1-to-1 if and only if IFF, if and only if t of x equals 0 has only the trivial solution. Come on. Questions?
Is this the only format that we can do the if only if problems?
You mean like the prove it one direction, then prove it the other direction?
Yeah, that's what I mean.
No, actually the next example does it the other way.
Oh.
It's a good question. Other questions? All right. Let's keep going. So theorem 12 says if T is a linear transformation from Rn to Rm and A is a standard matrix for T, then T maps Rn onto Rm if and only if the columns of A span Rm, and T is 1-to-1 if and only if the columns of A are linearly independent. And so notice what this is doing is it's connecting onto and span and 1-to-1 and linearly independent. So there's sort of like a mapping or a connection between these two concepts. So this requires two little proofs. So if we prove, so here's our claims. So if we're doing A, part A, we're going to assume that the columns of A span Rm. Okay. So in answer to Abed's question here, I'm going to do my if and only if statement all in one shot. So I'm going to say this is true if and only if. But what does it mean to span? It means I can get everywhere in the range. So if and only if there is a solution, to AX equals B for all B in Rm. Upside down A for all B in Rm. Like, this is what it means to span. And here we're using matrix properties. And now we want to see if we can connect the A matrix with the matrix of the linear transformation with the linear transformation itself. And so this is true if and only if, and we're just going to connect it back to the linear transformation T. There is a solution to T of X equals B for all B in Rm. Okay. So notice what I did is I'm starting in my A world, and now my A world has become the T world because I've gone from the vector world to the linear transformation world. But this means that I can get to every possible output in my codomain. So this is telling me that T maps onto Rm. That ends this little part of the proof. Okay. Let's do B. So B says T is 1-to-1 if and only if the columns of A are linearly independent. So in this case, I'm going to assume that T is 1-to-1. So if it's 1-to-1, somebody else, upside down A, what does upside down A mean? It means for all. Thank you. Okay. So assume T is 1-to-1. So this means, based on our proof we just did a moment ago, this means that T of X equals 0 has what kind of solutions? Has only the, which solutions from the previous theorem? From Matthew and Felix and Seche and Kevin, has only the trivial solution. Okay. And that's happening, here we're in the T world, now I want to go to the A world. So this means that AX equals 0 has only the trivial solution. Okay. So I started in the T world, still in T, and then I can go from the linear transformation world to the world of matrices. So I switch to the A. And now you have that AX equals 0 has only the trivial solution. This is something that we've worked with in the past. This tells us that the columns of A must be linearly independent. And so we've proved both of our little statements. And so if you want to end a proof, you could state the whole thing again. You could say, as was to be shown. You could say all those things, or you could be a cool mathematician. You could write QED. QED. Which has a lot of meanings. I think we've talked about this in class before, but it's like quod erat demonstratum, basically as was to be demonstrated. But it could also be, if you're feeling cool and cocky, it could mean things like quit neat dinner or quite easily done or things along those lines. So it's got lots of interpretations, but it comes from Latin, which means as we were trying to show. And there's the whole theorem and proof. Questions about this theorem 12? So that's the therefore statement. Yep, exactly, Andrew. Yeah, exactly. So rather than saying therefore T maps Rn onto Rm if and only if, and T is 1-to-1 if and only if, we could just say QED and save ourselves some writing.
Since you did this question, F and only F questions in one shot, could we have done that the same thing on the past example?
Not really. You mean where we're doing the statements both directions? Is that that's what you're looking at?
Yeah, that's
right. It sort of depends on the type of statements you're using. So sometimes you can, like in this case, where the statements basically are interchangeable, but in the previous example, the logic we were doing in one case wasn't reversible. And so this approach only works if things are reversible. Does that make sense? I think about it maybe by analogy. Think about when you're solving equations and or when you're simplifying. Sometimes you'll simplify and you'll have like a x times x plus 1 divided by x plus 1. And so you get that you could cancel out the x plus 1s. But if I just gave you x, it would be difficult you could go from the first line to the second line, but going from the second line to the first line, that's not very obvious. So that's by analogy. All right, let's look at a couple of simple examples and make sure you're tracking out how this all plays out. So I want to point out that in the first matrix, you have 1, 2, 3 pivots. And so in this first case for A, we could say A is onto. It's onto R3. And it's going to be onto R3 because you have 3 linearly independent columns in R3. Or 3 pivots in R3. And the fact that these are 3s is mattering, that they match. Okay. Is it 1-to-1? No. So no, it's not 1-to-1. There's too many columns. Okay. In the second case, we could say, is B onto? And you could say, no, not enough columns. There's not enough columns to span R3. You only have 2 columns in B. And so you'll never have enough. Doesn't span the gap. Okay. And then in looking at B, are they one-to-one? Notice that up here that the columns are not multiples of each other. So they are linearly independent because there's only 2 of them. So we would say yes, the columns are linearly independent. The first one was a no, or was a yes. Okay, so what I want to point out in all this is that with onto or span, you have to have enough. So to span, you need enough vectors. Right? And if you look at this box, notice you need enough. And here I said there was not enough vectors. And then to be one-to-one, you can't have too many. So you can't have too many vectors. And you'll see here the too many vectors and the too many vectors right there showing up. So to span, to be one-to-one, this first one also ties to onto. Sorry. And the second one ties to linear independence. Sorry, trying to connect all of our concepts together. Questions?